In this video, we're going to be talking about current, electricity. Okay, now in our other videos or playlists, we talked about static electricity and everything that comes with it. Okay, we talked about Gauss law, talked about electric potential and the likes. Okay, now those videos that we talked about, they all have to do with charges that are at rest. Okay, now for current electricity, we're simply talking about charges that are in motion, that is, the charges are now moving. Now when charges are moving, what they create is what we call current or electricity, which we all know in general. And it is important to take note that current is being caused by mobile or free electrons. Okay, charges that are moving by mobile or free electrons. Okay, that is what causes current. Now we're having a diagram on the board. Okay, and this is a diagram of a conductor or a wire when viewed in its micro state. Okay, a very small scale. Okay, now it is cylindrical in shape, and we're going to consider a section of it. Okay, we're going to consider a section of it. Now let's say from here to here, a very small section, okay, which we are going to call delta x because it is very small. Okay, we're going to call that delta x. And then okay, now these guys are charges in this conductor. Okay, now at normal room temperature, what you notice about the charges in this conductor is that they are moving freely, colliding with themselves and also with the walls of the wire. These are the charges, okay? The free charges, they are moving freely. Now, the maximum velocity at room temperature that they will use in moving, okay, these charges, is called the terminal velocity of the electrons or the charges rather. Okay, so when there is no potential difference applied, the wire is just there, okay, at normal temperature. The velocity they use in moving is what we call terminal velocity. Now something now occurs when we now apply an EMF, of which an EMF simply means electromotive force. Okay, we're applying a force electrically. Okay, we're applying a force that will help these charges move through the conductor. Okay, they are moving freely. When we now apply a force, they now start working now moving in one direction. So we're applying an EMF between the ends of the conductor. What happens? We are creating a difference in potential. That is, one place has higher potential, one place has lower potential. So that EMF we're applying will help us move the charges from a higher potential to a lower potential. Hence, current is being produced. Okay, so first things first, current is the rate of movement of electric charges. Okay, so current is equal to the rate of movement of electric charges, that is change in Q over change in T, of which some persons will just write Q over T depending on the context you are making use of. Okay, so in this case we're going to make use of both, and you'll notice that in this diagram it is a very small scale, so we might want to make use of delta Q over delta T more often. Okay, now we've said that after applying an EMF to this conductor, what we'll notice is that these charges will now be moving in one direction, okay, due to the EMF. So if I'm applying the EMF between here and here, what we'll notice is that, okay, this guy starts moving in this direction. Now here is the definition or the formula for solving for current. Current is equal to delta Q over delta T, or Q over T. Okay, but then again, what is current, or how do we define current? Okay, how do we define current? Now we can simply define current as the rate of movement of charge with time, okay, in the conductor. That is also very much acceptable. Okay, but then the basic or the first instance that helps us show what current looks like or what it talks about was when an experiment was performed between two wires, okay, placed at a distance of 1 meter from each other in a vacuum. Okay, so when we're having two wires like this, okay, two wires, I will place them at a distance of 1 meter from each other. Okay, it gets to a point, as current flows in the same direction, it gets to a point that the attractive force, of which this is something we talk about in magnetic field, that the attractive force between these two conductors will equal a value of 2 times 10 to the power of minus 7 newtons. Now when the value of the force of attraction of these guys, when they are placed in a vacuum, placed at a distance of 1 meter, equals 2 times 10 to the power of minus 7 newtons. Okay, when the force of attraction becomes this guy, then we say that the current flowing through the material or the conductors is equal to 1 ampere. That is what we're talking about. So when this is the force of attraction between these two guys, we can now say that the current flowing through each of these conductors is what now? 1 ampere. That is the first definition, of which it was now broken down to I equals Q over T, rate of movement of charge. Okay, so either of both definitions are correct. It all depends on the context or what you are dealing with. Okay, so that one is for 1 ampere. Okay, you know current is measured in amperes or in coulombs per second. So 1 coulombs per second is equal to 1 ampere. 1 coulombs per second equals 1 amperes. Okay, don't mistake this for Armstrong. Armstrong has a degree on top. Okay, now considering this conductor, after we've now applied an EMF that will help this charge or force them to move in one direction, the velocity that they are going to be moving with, the velocity that these charges are going to be moving with in this conductor is no longer the terminal velocity. Okay, it is not called the drift velocity. I'm going to call it V with a subscript of D to tell you that V is the velocity and D represents what now? Drift. So we are forcing it to move in one direction, hence you now have a new velocity which we call the drift velocity. Okay, and of which we know drift velocity or our normal velocity is still change in distance with respect to change in time. Okay, the reason I'm including change because we are still considering a small section. So the section we're considering in this place is what now? Delta x, not the whole length of the wire. So we're having change in delta x with respect to what now? T. Okay, so from here we can now see that delta x 1 cross multiply is drift velocity times the change in time. Okay, let's call this equation 1 because we're going to do some substitution. So I'm going to call that equation 1. Now another thing we want to consider, this section of this conductor has a volume, right? It is cylindrical in shape, even in the small scale. It has a volume, of which we do know that the volume, okay, of a material is equal to mass divided by the density of the material, right? And then for these charges we are having, we are going to consider the molecular mass, of which I'm not going to say capital letter M divided by the density. So we're considering the molecular mass at this small scale, not the mass of the conductor. Okay, that is another thing we should take note of. So from here, volume is what now? Capital letter M over rho. Now, also something we should consider, okay? There is also something we should consider, or let's just call this equation 2 first. What we want to consider is the number of charges per volume in this conductor. Because we cannot just say, okay, number of charges in this conductor, we are considering a section. There's no way we're going to find that. But we can work with the number of charges in a section, which is the number of charges per volume. Now, if we call the number of charges per volume n, small letter n, we can now say that the number of charges per volume n, okay, is equal to NA, which is Avogadro's number of charges, okay, divided by volume. Okay, I can as well write it here, number of charges, okay, the number of charges divided by the volume. Now this number of charge, I can't replace it with n, so let's just say okay, let's just say I call it x. Okay, let's say the number of charges, okay, in the conductor is x. Okay, because it's not all the time that the number of charges is going to be NA, except we are considering 1 mole. Okay, so let's just say the number of charges is x. So n is equal to number of charges per volume of the conductor. Okay, now another important formula that we talked about in static electricity is Q equals NE. Okay, we know that from charge quantization, Q is equal to NE, or rather let's make use of big Q. We could say that Q is equal to NE, right? But then again, these two N, they are different. This one talks about just the number of charges, while this one talks about number of charges per volume. So instead of using N here, it is important that I replace it with X. Okay, I replace with the X so that you don't mistake X and N. Okay, so if you are dealing with static electricity, you can as well make use of what now? Just N, because we know that N will not represent number of charges per volume. But since we know that we already represented N as number of charges per volume, let's represent that with what now? X. So I can now say that Q is equal to what now? XE, of which X is what? Number of charges. So if I say that the number of charges per volume is equal to what now? NA over V, and is equal to N. We can then what now? Make use of some substitution. Okay, and then again, from delta X is equal to VD times delta T, we can also substitute, right? But before that, let's substitute for this volume. Volume is M over rho, right? So I can now say that N is equal to NA divided by V, and then I'll put this guy inside. So if I substitute into here, I will get number of charges per volume is equal to NA divided by V becomes big letter M over rho. So I'll have big letter M over rho. And if I do that substituting, I'll get NA times rho divided by capital letter M. Okay, so N is equal to NA times rho divided by capital letter M. Okay, next thing I want to do is substitute. We want to substitute that guy into what we're having here. Okay, so from here we notice that X is equal to N times V, right? So X is equal to N times V. If I substitute in there, okay, we know that X is equal to, I'll write it here, but X is equal to N times V, of which V here is the volume. If I substitute in, I'm going to get Q is equal to NV times E, right? Makes more sense. And then again, V is area times distance now, right? V is area times distance, okay, of which this V here is volume. But V here, which is volume, okay, volume is equal to area times distance. Now the distance we'll be considering is what now? This small distance, which is delta x, okay, times delta x, and we're substituting that, we get Q is equal to N times area times Vx times E, right? Oh, this should be delta x, rather. It should be delta x, okay, times delta x times E. That's what we're going to get. And then again, we still haven't substituted for Vd times delta x times t, okay? Now from here, we can make delta x a subject formula. If we make delta x a subject formula, we get delta x is equal to Vd times delta t. And when substituting that, we get Q equals Na, okay? Delta x is delta Vd times delta t, okay? So we're going to get V with the substitute of d times delta t, isn't it? Times E, of which E is the charge of the electron. Yeah? Now we did say that current is rate of charge, okay, or rate of change in or movement of charge. And this current is delta Q over T. If I choose to substitute in that, I'm going to get, dividing both sides by delta T, I'm going to get Q over delta T is then equal to Na, okay, Na times Vd times E, right? Okay, Na V with the subscript of D times E. So we have the number of charges per volume. Now, Q over delta T is simply current, which you explained here. Delta Q over delta T is current. So we can now substitute. What we have here is current. So current is then equal to N times A times V with the subscript of D times E. Okay, this is one important formula for solving current. And then we can divide both sides by area. When we divide both sides by area, we are going to get current over area is then equal to N times drift velocity times E. Okay, now current over area is what we call the current density, that is current divided by area. Okay, so what we have here is called current density and it's represented as J. Okay, it is called current density. Now current density is measured in amperes per meter squared. So if we represent it as current density, we're going to have J equals N times Vd times E. This is what we're going to have. Okay, so J equals N times Vd times E. This is what we call what now? The formula for calculating current density. Now there's a whole lot to talk about on that current density, which we'll talk about in our future videos. Okay, for now we're going to pause at current density. So it is important to take note of these two formulas, this one here and this one here. Okay, we have I equals NAVD times E. We're going to be solving the problem on these two formulas as well. Okay, and then we have J, which is current density, equals NVD over E. Now it's important to take note that the N there is not the number of charges, okay, but rather the number of charges per volume. Number of charges per volume is Na times rho divided by what now? Molecular mass. Okay, so here N is equal to Avogadro's number times the density divided by the molecular mass. Okay, So these are the useful formulas. Okay, like I said, in our next video we'll be solving the problem on this to help you understand how we make use of these equations that have been derived. Okay, so do it to like, share and subscribe to the YouTube channel. And if you have a question, put it in the comment section. Always feel free to do that. See you in our next video. Bye.